A piston cylinder device contains 50 kg of water at 250 kilopascal and 25 degrees C. Let's call this state number 1. The cross-sectional area of the piston is 0.1 meter squared. Heat is now transferred to water, causing part of it to evaporate and expand. When the volume reaches 0.2 meter cubed, the piston reaches a linear spring whose spring constant is given. I'm going to call this state number 2 when the piston reaches the spring. More heat is transferred to water until the piston rises 20 centimeters more, and let's call this state number 3. Determine the final pressure and temperature. The work done during this process. Also show the process on PV diagram. I see a nice image of the cylinder piston devices given, but I would like to draw the system myself for each of these single states to make sure that I'm not missing anything. So state 1, a cylinder piston device is given. This is a state 1. Mass of water is given. M1 is 50 kilogram. Pressure is given 250 kilopascal, and temperature is given 25 degrees C. Then heat is transferred to water. We are going to have heat input to the water, causing part of water evaporate and expand. So we have the same cylinder piston device. We're going to have expansion of water. When the volume reaches 0.2 meter cubed, the piston reaches a linear spring. So let's say we have a linear spring here. Problem says that the piston reaches the spring, but it's not going to compress the spring. So this is state number 2. Volume in state number 2 is given 0.2 meter cubed. More heat is transferred to water. You're going to have more heat until the piston rises 20 centimeter more. So state number 3, the piston rises 20 centimeter more. Let's call this delta X, 20 centimeter. Now the spring is compressed. This is state number 3. Determine the final pressure and temperature. I'm interested in P3 and T3. The work done during this process. So let's call this process 1, 2, and let's call this one process 2, 3. So I'm interested in work or boundary work, which is W during process 1, 2 plus the work during process 2, 3, and show the process on a PV diagram. So I'm going to take all the water in the cylinder below the piston as my system. I see that it is a closed system because no additional mass is going to the system or getting out of the system. Let's start from state 1. P1 is 250 kilopascal. Moving on to state number 2, I see that the piston is free to move, so the pressure should remain the same. In state 1, this is going to be the free body diagram of the piston. In the free body diagram, we draw all the external forces and moment applying on the object. What do we have? We have pressure in state 1 times cross-sectional area. This is going to be the force of the water applying on the piston. You are going to have atmospheric pressure times area, and we may have the mass of the piston times gravity, which is actually the weight of the piston, because we are not sure if the piston is massless or not. Write down the equilibrium equation, or Newton's second law. Sum of forces in y direction equals 0, or P1 equals P atmosphere plus the weight of the piston divided by the area of the piston. And pressure in state 1 is given 250 kilopascal. Moving on to state 2, I can draw the same free body diagram for the piston. State 2, the same free body diagram for the piston. In state 2, we have pressure of water in state 2 times area of the piston. Over here, we have atmospheric pressure times the area of the piston. We are going to have again the weight of the piston. And we know that in state 2, piston moves up and it reaches the spring, but it is not going to compress the spring. So we do not have a spring force applying on the piston. Again, equilibrium equation, sum of forces in y direction is 0, or P2 equals atmospheric pressure plus the weight of the piston divided by the area of the piston. I see that this is equal to the equation above, so P2 equals P1. And we know the number for P1, 250 kilopascal. So again, during process 1, 2, pressure remains constant because the piston is free to move. Then let's move on to state number 3. Draw the free body diagram of piston one more time. What are the forces? Pressure in state 3 times area of the piston, atmospheric pressure times area of the piston, the weight of the piston, and I see that piston rises, compresses the spring, so we have to have the spring force applying in opposite direction. Spring force. Again, equilibrium equation, sum of forces in y direction equals 0, or P3 equals atmospheric pressure plus the weight of the piston divided by area plus a spring force divided by area. If I look at this equation, I see that the first two terms equals P1 or P2, which is 250 kilopascal. So P3, or the pressure of water in state 3, is 250 kilopascal plus a spring force divided by the area of the piston. Area of the piston is given in the problem statement. What was that? It is 0.1 meter squared. And a spring force is K times delta X. K is given in the problem statement. It is 100 kilonewton per meter. And delta X is the compression length in the spring. We know that the piston moves up 20 centimeters. It is like it's compressing the spring 20 centimeters. So that is going to be our delta X. 0.2 meters, and one more time, K is given 100 kilonewton per meters. So if I solve for pressure, pressure in the final state will be 450 kilopascal. Please double check the units. Make sure that you use correct units. So we just calculated pressure in the final state. Let's move on to the temperature in the final state. Pressure is given 250 kilopascal and temperature is given 25 degrees C. We can determine the state. So for example, at the given pressure, I can go to the pressure table. I can read for Tstat. Tstat at 250 kilopascal is 127.41 degrees C. I can compare this number with the given temperature, 25 degrees C. I see that given temperature is less than Tstat, or the state is subcooled or compressed liquid. So specific volume in initial state is almost equal to a specific volume of saturated liquid at the given temperature, 25 degrees C. And if I have this number, I can multiply it by mass and get volume in the initial state. Then moving on to state number 2. Pressure equals P1, which is 250 kilopascal, and volume is given in the problem statement. So again, I just need to determine the state. Based on the definition of a state postulate, we need two independent intensive properties. Extensive property or volume is given, so I'm going to convert it to intensive property. Specific volume is volume divided by mass. We are dealing with a closed system, so mass remains constant. This mass equals M1, which is 50 kilogram. 0.2 meter cubed. Sorry, this was meter cubed. Divided by 50 kilogram, which is 0.004 meter cubed per kilogram. So pressure is given, a specific volume is given. I know that saturated mixture table serves as the reference for us. At the given pressure, 250 kilopascal, I can go to saturated mixture table. I can read for VF and VG and then compare these numbers with. I see that the specific volume in state 2 falls between VF and VG, these two numbers, so state 2 will be saturated mixture. Then moving on to state 3. Pressure in state 3 is 450 kilopascal, and in state 3, let's see what we have. Problem says that in state 3, the piston moves up 20 centimeters with respect to the location of the piston in state 2. So the volume of water in state 3 equals volume of water in state 2 plus this additional volume, which is the cross-sectional area of the piston times the height, which is 20 centimeters. Right? So we have volume in state 3. Volume in state 3 equals volume in state 2 plus cross-sectional area of the piston times 20 centimeters or 0.2 meters. And then specific volume will be volume divided by mass. Again, we are dealing with a closed system where no additional mass gets to the system or leaves the system. So mass remains the same and it is 50 kilogram of water. We can solve for a specific volume. Everything is given. It is going to be 0.0044 meter cubed per kilogram. Now again, I need to determine the state. At the given pressure, which is 450 kilopascal, I will go to saturated mixture table and I'm going to read for a specific volume for saturated liquid and a specific volume for saturated vapor. Compare these numbers with a specific volume in state 3. I see that the specific volume in state 3 again falls between VF and VG. So state 3 is also a saturated mixture. State 3 is saturated mixture, so temperature in the final state will be Tsat at the given pressure, which is 450 kilopascal. And this number is 147.9 degrees C. So we just solved for the temperature in the final state. So part A is done. Let's move on to part B. We have to determine the total work during these processes. So I see we have process 1, 2, and we have process 2, 3, and the total boundary work is the work during process 1, 2, and the work during process 2, 3. Boundary work is defined as integral of P dV, or it is the area under the curve in PV diagram. So I just need to draw a PV diagram, and then the area under the curve in that diagram will give me the total boundary work. So let's draw the PV diagram because we know the pressures and volume in all of the states. Y-axis is pressure in kilopascal, and x-axis is volume in meter cubed. I draw a dome. State 1 Let's see. State 1 was compressed liquid, and based on the assumption to solve for the properties, we can assume that it is saturated liquid at the given temperature. So state 1 is actually saturated liquid somewhere here, and pressure was 250 kilopascal. Volume in state 1, where is the volume? I actually need to solve the volume here. Volume in state 1 is 0.05 meter cubed, 0.05. Then state 2 is saturated mixture. Pressure is 250 kilopascal, and volume is 0.2 meter cubed. Pressure remains the same. So this is going to be process 1, 2. Moving on to state number 3. State number 3 was again saturated mixture. Total volume from this equation is 0.23 meter cubed. So let me see. 0.22 meter cubed, and the state is saturated mixture, so it has to stay under the dome. But I see that pressure increases to 450 kilopascal. So let's say somewhere here. So let me change my dome because I do not have enough space under the dome. And let's change this B somewhere here, 0.22. Because during process 2-3, a linear spring is involved, the relationship between pressure and volume will be linear. So this line will be process 2-3. This is going to be our PV diagram, and the area under the curve will give us the total work. So this area, the area of this region, and this one will be the total work. Let's write it. Boundary work or total boundary work is integral of PdV, or the area under the curve in PV diagram. It is actually the boundary work during process 1-2 plus work during process 2-3, which is actually this area plus this area. Okay, so we have 250 kilopascal times 0.2 minus 0.05 meter cubed plus the area of the trapezoid, which is half of the first base, 250, plus the second base, 450 kilopascal, times the height, which is 0.22 minus 0.2 meter cubed. And at the very end, we know that 1 kilopascal meter cubed is 1 kilojoule, so we do not need any conversion factor. The total boundary work will be 44.5 kilojoule. A specific volume in state 2.